Data engineering is often described as the backbone of modern software systems. We build pipelines to move information from one place to another, ensuring that business logic runs smoothly and reports are accurate. But there is a specific nightmare that haunts every engineer working with distributed systems. It is the phantom duplicate. You run a job, it processes data, and then you run it again. Maybe because of a network glitch, maybe because of a manual retry. Suddenly, you have two records where there should be one. This is not just a minor annoyance. It corrupts your analytics, it skews your financial reports, and it erodes trust in your entire infrastructure. Here is the thing about designing idempotent pipelines. Most engineers think the solution is simply adding a unique identifier to every record. They call it an idempotency key. You generate a token, you check if it exists, and if it does, you skip the work. It sounds logical. It works in isolation. But in a distributed environment where retries happen automatically and messages can arrive out of order, that simple key is often not enough. We need to move beyond checking a flag and start thinking about the state of the data itself. Consider the most common pattern for updating data. It is the delete and insert method. You query the system, remove the old record, and then insert the new one. If the job fails halfway through, you are in trouble. If the delete happens, but the insert crashes, you have lost data entirely. If the insert happens but the delete fails, you have duplicates. This pattern relies on the assumption that both steps happen atomically. In a distributed system, that assumption is often false. We need a way to handle retries without losing data or creating duplicates. The solution lies in using upserts. An update or insert operation is a single atomic action. You tell the database to update the record if it exists, or create it if it does not. This ensures that running the job 10 times yields the same result as running it once. But this only works if you are using the correct key. A database auto-increment identifier is useless for idempotency because it changes every time. You must use a business key. This is a unique identifier that comes from the source system, like an order number or a customer identifier. It represents the real-world entity, not just a database row. Now consider the problem of out-of-order messages. In a distributed system, message A might arrive before message B, even if A was sent after B. If you process them based on arrival time, you might update a record with stale data. This is where sequence-based reconciliation becomes critical. You need to attach a sequence number or a timestamp to every piece of data. When the pipeline runs, it does not just check for existence, it checks the version. If the incoming data has a lower version number than what is currently stored, the pipeline rejects it. If it has a higher version number, the pipeline applies it. This ensures that you always move forward in time and never overwrite newer information with older information. There is another layer to this complexity. Schema evolution. In a real-world environment, your data structure changes. You add a column, you rename a field, or you split a table. If your pipeline is not idempotent regarding schema changes, you risk breaking the pipeline when you try to reprocess historical data. This requires a design where the data model is stateless and replayable. You treat the pipeline as a function that transforms input into output. The input is the source data, and the output is the target state. You do not care about the intermediate steps. You only care that the final state matches the current definition of the data. To handle this safely, many modern systems use soft deletes. Instead of physically removing a record, you mark it as inactive. This allows you to reprocess old data without worrying about deleting active records that might have been updated by a different process. You combine this with versioning. Every record carries a version stamp. When a conflict arises, the system uses the version stamp to decide which record is authoritative. This prevents concurrent updates from overwriting valid changes made by another process. Looking forward, the industry is shifting towards declarative pipelines. Tools like Lakeflow or similar modern frameworks are changing how we approach this problem. Instead of writing custom logic to handle every edge case, you define the intended state of your data. The system automatically handles the retries, the deduplication, and the reconciliation. This reduces the burden on the engineer to write error handling code for every single transaction. It moves the complexity from the application layer to the orchestration layer. There is also a growing trend involving agentic artificial intelligence. In the future, we expect pipelines to become self-healing. An agent could detect an idempotency violation, analyze the logs, and automatically correct the state without human intervention. This is not science fiction. It is the logical next step in data reliability. If the system knows the intended state, it can figure out how to get there even when things go wrong. This shifts the responsibility from preventing errors to recovering from them gracefully. Ultimately, effective idempotent design requires a shift in mindset. You stop trying to make the code retry safe and start designing the data model to be stateless and replayable. You ensure that running the same job multiple times yields the exact same final state. This is not just a technical choice, it is a philosophical one. You accept that failures will happen. You accept that messages will arrive twice. You design your system to absorb those shocks without changing the outcome. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.